All right, so we're going to do it's number 13 or 3.49. So we use just our standard form here. Remember, folks, you don't have to pay attention, so don't be a distraction to me or to those that are following along. I'm kind of in the middle of something here. That's okay. So you would need, in your Y here, you should have shown some understandings. That's one thing you need to understand to do this problem. Yeah. Okay. So both girls' position constantly changes. What must be true for her to catch her friend? No. Not a requirement of the universe to catch someone to be accelerated. Think about if you want to meet somebody, what piece of information do you give them? Same place, same time. So, yes, she may have to speed up. She may have to go around the other side of the world to catch whatever she has to do, but they have to be at the same place at the same time to catch. You gotta, don't forget kind of the base of to catch. So to meet must be same place, same time. Because she could be going faster, she could be going slower, she could accelerate. None of those make it possible for them to meet. They may be what has to happen to get to the same place at the same time. But the key here is same place, same time. I might even draw a little diagram just to remind myself kind of what's going on. Let's see, we had, oh good, bikes. Yeah, those are so much fun to draw. And let's see, what do they tell us about these bikes? Friend rides by at a constant speed. So we got her moving this way at 4.1 meters per second. Constant. 2 seconds later, she hops on her bike and accelerates. At, what was that? 2.2? Remember, your numbers may be different. So look at your own problem to make sure that you're using your numbers. And then they want to know how much time from the moment she hops on her bike does it take until she catches up. So in this one, and they said, let's see, sorry. So they pass each other at 0 seconds, and she hops on her bike at 2 seconds, timeline-wise, right? Yes? And then they're going to travel some distance until they meet up again. So I almost want to draw like a little, we have the first location here. When they pass each other, that's t equals 0. And then sometime later at 2 seconds, this friend has moved to here. The red one hasn't started moving yet. And then later on, at some time, the two of them have met up again. And let's see. I just want to look at all their questions. I may end up answering these out of order, right? Oops. Let's see, how much time till she catches up? How far does she travel in this time? What is her speed when catching up? Okay, so I want to examine here, and they're interested more in the time that she travels. So let's look at two ways. Let's look at your friend. So your friend, and we're going to use d equals d naught plus v initial delta t plus 1/2 a delta t squared from our equation sheet, right? And the friend, let's call this, we'll call time t sub e, time at the end. And I know that at that time, both of these, you and your friend have to be at the same location at that time. So, which way do you guys want to call positive? To the right? Okay. And you okay with here at time equals 0, d equals 0 also? Yeah? Okay. You know, for those of you that forgot to do these, great time to be on the computers and working on them. Absolutely fantastic time for that. Or you can just sit there and that's not as good, but so the friend is gonna end up at the distance at the end, started at 0. Her initial velocity was at 4.1 meters per second. Traveled it for some delta time, and she has no acceleration. So do I even need to write that last term? No, because what's 1/2 times 0? And then times t squared? 0. Okay, good. And that delta t, I'm going to take this one more step. So this is the 4.1 meters per second. The delta t is going to be, remember, delta is always final minus initial. So that's going to be time at the end minus the initial time, which is 0. So that's how far the friend has traveled. How far you've traveled, so this is now you. We're going to use the same equation. Right? And you're going to end up at the same place, d sub e. You're going to start at 0. Your initial velocity now is 0 times delta t. But you're accelerating at 2.2 meters per second squared. And your delta t, you're going to end up at t sub e of minus 2 quantity squared. Because remember, you don't start moving till 2 seconds has passed. Yes? No? Okay. So, we can set these two like equal to each other. Try this a little simpler. dE equals 1/2 times 2.2 meters per second squared. dE minus 2 squared. And now let's see, they want to know what the time is, right? See all their things, I keep forgetting what they want to know. How much time from the moment she hops on her bike until she catches up. And then how far does she travel in this time? So what they really want is they want t minus 2. Maybe we should express it a little bit differently then. Why don't we call, let's shift our time here. Let's say that rather than this being at t equals 0, let's call our 0 time here. What would that make this time? If we shift 0 time to here? Negative 2. I know it seems like a really weird thing, but watch what's going to happen. So rather than 0 up here, we have minus, we have t sub e minus a negative 2 seconds. And down here, we have t sub e minus 0 squared, which just comes to t sub e squared. So that's the only thing it does to us. Yes? So that might make life a little simpler because this one is squared and that one isn't. So let's bring those two together, see if we can find the time. So I'm going to write, oh, they're both equal to the same thing, right? Oh, so we can set them equal to each other. So we can do 4.1 meters per second TE plus 2 seconds equals 1/2 2.2 meters per second squared t sub e squared. Oh. Which 2 seconds? Well, I had said back up here that the distance she travels is her velocity times the change in time. The time she travels from, she starts traveling at negative 2 and continues until t sub e. So the delta time is t sub e minus negative 2, which is same as plus 2. Oh, that looks like some less than happy math. So you know what I'm going to do is I'm going to put it in, I'm going to use Wolfram rather than, I don't like algebra, right? So let's grab Wolfram here. Let's see, where do I see here? Down at the bottom of our site where it says Math Solvers. I'm going to grab Wolfram. Enter what you want to calculate. So let's 4.1 times t plus 2. So 4.1 times parentheses t plus 2 equals 1/2 times 2. So 0.5 times 2.2 times t squared. Yes. And it tells me my solution is either negative or positive. So the positive is 5.17. Let's see if that's right. Huh? I use t rather than t sub e. Yep. it's a window, so you can bring it up partially. So I picked the one that logically made more sense, which was 5 seconds, because the other one isn't moving yet at that first time. That's what I did in my answer. Yep. That was my part A. Yep. And then how far did she travel during this time? I can go back and use what I've already done to do part B. So let's see, which one are they asking? How far did she travel this time? Okay, it's the bike first. So I'm gonna use this answer time with this is part B now. And I'm solving for D sub E. 1/2, 2.2. And then my time, 5.16934 seconds squared. And I find out how far she has traveled. And then on to part C, they ask me, what's her speed when she catches up? So I'm going to I'll look back at my equation sheet, pull out that V final equals V initial plus A delta T. And I want to know V final. How fast is how fast are what we refer to as U going at the beginning? 0 plus 2.2 meters per second squared. My delta T is the 5.16934 seconds. Yeah. And I just find V final. Yeah, so finding the time was the trickiest part. And then I'm just using that time to other instances to so started this number 12 or 3.86 about the spaceship getting shot out of a cannon. This is one part of our why probably would be good to be a force diagram. Wouldn't take off if it didn't have one, but it would be better if it did. So one thing where I would start off, let's see, was it 3.86? I'd start off with that impulse causes a change in momentum. I think is where I'm going to start with this. Let's see. Actually, I'm not going to start there. Sorry. I'm going to back up off of that. Because if we do it with impulse, we need to know the amount of time it spends in the barrel. And we don't know that. So I'd probably start off focusing in on acceleration, is the rate velocity changes. The longer the barrel, the lower the acceleration. And how about the acceleration is caused. And do we even need that? Let's see. No, we don't even need that. I was wrong. This one doesn't need a diagram. What I might draw is my cannon, and that this distance, we say it starts at 0 meters. This end is what, 213? And oh, we know what's its initial velocity. I bet your initial velocity is not. That's its final velocity. 0. Yeah. It is about the spaceship. It's about how it accelerates as it's being shot out of the cannon. And that's where the author, we said the author made a slight here where they said the spaceship is. It should have said the cannon is approximately this long. They're talking about the I think it's called like Trip to the Moon or something like that, where he basically envisioned a train, Jules Verne envisioned a train being shot to the moon. All right. So and then at the end, I've got 1.24 times 10 to the fourth, which is 12,400, right? So at the end here, mine's going 12,400 meters per second. And I want to know what's the acceleration experienced by the travelers. Okay. So I'm going over here to my, now I'm going to use that V final squared equals V initial squared plus 2A delta D. And the A should have that set. So I know my final velocity, 12,400 meters per second. That's squared. My initial velocity was 0. 2, I don't know what A is, so I'm just going to leave that as A. And my delta D is D final minus D initial, so 213 meters minus 0 squared. And then I'm just going to solve for A, right? Okay, so I need to pull out my calculator. And do yeah, so I didn't bother. And I get 3,390 meters per second squared. That seems rather large. Let's see if that's right. Yeah, but I left off the 2 when I grabbed my calculator real quick. I should have put in my calculator is the 12,400 meters per second squared over 2 times the 213 meters squared. That equals A. So basically, I should have gotten 1690 instead. And I bet that will be right. All right, that one. Nope. No, because the 2 is multiplied by A and multiplied by the 213. Put down a number. Yep, 215. Okay, this is where it's being a pain. It only wants 2 sig figs. What I forgot to do is that the 213 isn't squared. Why did I square the 213? So it's just 213. So yeah, when you mess up the squares in an equation, it kind of comes back to get you. So you should get a huge number. Let's see if that's right. So 3640. Yay!
What was your number? Was it really big? Like.
Yep. 360,000 is what I got. Meters per second squared. Oops. Alrighty. That was enough tries on that one. Next time.